And there are two types of approaches in studying the systems. There are microscopic approach and macroscopic approach. Whatever we are doing is a microscopic or macroscopic approach. If you want to have microscopic approach, and that is if you want to study the properties of the substance at molecular level, then this will not work. We have to go to what's called a statistical method. And in the similar way, the classical thermodynamics is limited to the systems with low velocities. And if the velocities of the systems approach velocities of light, again, the classical approach will not work. You have to go to relativistic mechanics. In the same way, if you go to, as I told, the molecular level, we have to study what is called a statistical thermodynamics. Microscopic approach needs statistical thermodynamics. In the same way, again, if you go to elementary particle level, then again it will not work. We have even statistical thermodynamics will not work. We have to go to what is called as quantum mechanics. Okay, we have to see such limitations like again conservation. So whether mass is conserved and energy is conserved, so every one of you will say yes, sir, mass is conserved, yes, sir, energy is conserved. But is it true? We know from Einstein's mass-energy relation, E equal to mc square. That is, mass can be converted to energy and energy can be converted to mass. Then how can you say mass is conserved and energy is conserved? We say actually mass energy is conserved together, but not independently mass and independently energy. But here, when you study fluid mechanics or thermodynamics or heat transfer, we say mass is conserved and energy is conserved, assuming that there are no nuclear reactions. So in that way, we make many assumptions. We study in detail. Then system and control volume. So we have to define a system when you start studying something, right? So we have to define a system. So what is that we are focusing on? So that is called a system. And every system is bounded by a boundary. And so based on whether it is what mass flow is there, energy flow is there, we say it's closed system, open system. Open system is also called as control volume. So like that, you already have studied, but we go in detail with beautiful examples. And the dimensions and units. This is very important because thermodynamics deals with a lot of properties and also a lot of equations. And when we solve the equations, we have to be very careful about the units and dimensions of each and every variable that you are using and each and every term that you are using in the equation. And we study about what is force, what is weight, what is state, what is path, what is the process, what is isolated system, what is adiabatic system, like that. And also we study about various properties. And then thermodynamic equilibrium. So there are various types of equilibrium you might have learned, like mechanical equilibrium, thermal equilibrium, chemical equilibrium. When all the equilibriums together are existing, then we call the system to be in thermodynamic equilibrium. Then thermodynamic definition of work, different forms of work. And so we have learned about work in mechanics as force into distance. But there can be work transfer even if there is no distance or no movement of the body, still there can be a work existing. So what types of things we can call them as work? So there is a wide range of examples for thermodynamic definition of work. And then we study about point function and path function, and then heat, temperature, and zero law of thermodynamics and thermometry. So you know that thermometry is based on zero law of thermodynamics. So these things we discuss in the second chapter. And the third chapter, we got the first law of thermodynamics, which we are very familiar. And yeah, so it is applied to a closed system and the open system and to a process or to a cycle. So we use the first law for various examples. And the concept of nature of energy, internal energy, and that is stored energy or energy in transit. And I was talking about two substance and two property rule. And two property rule was also called as state postulate. And then firstly apply to control volume, that is when there is a flow of mass taking place. how the first law is getting modified. And the general energy equation we study and steady flow energy equation on unit mass and time basis. Then applications of steady flow and energy equation to boiler, turbine, heat exchangers, pumps, nozzles, etc. We study. Just if you see some of the examples, energy balance of boiler, energy balance for a compressor, so you can see what is entering, what is leaving, mass balance, energy balance we study. And for energy balance for a turbine, for a heat exchanger, and to a nozzle, to a pump. We'll go in detail and we'll see what are the equations. And because we have various equations to be solved, we have to solve for some variables which are not given. You have to be careful about dimensions and units, and you have to check for dimensional homogeneity. And then we go to the second law. So before going to the second law, we will see why we have to go for second law. What are the limitations of the first law? And then in the second law, we learned about heat, we learned about heat engine, heat pump, and refrigerator like that. So we will define here what is efficiency, what is coefficient of performance of heat pump and refrigerator, how they are related. So these things we study. And then thermal efficiency and coefficient of performance. Then we see the second law statements. So there are two statements given, and one is given by Kelvin and Planck, and another is given by Clausius. So these statements look entirely different if you see at the statements, but they are proved to be equivalent. So that we will do later. And then Carnot theorem and corollaries. So we will see there is a particular cycle or region which is an ideal one and which we can give the maximum efficiency. And this is like a benchmark whenever you construct an engine. And if you want to find out the performance of it, we always compare it with the Carnot cycle so that we can see how good it is. And the Carnot theorem has some corollaries coming with the theorem, and some additional understanding we can have of the Carnot theorem through corollaries. Then we will define what is reversible process and irreversible process, and then Carnot cycle and thermodynamic temperature scale. This comes in corollaries. And then we define an important property called entropy. I think up to this Clausius theorem, inequality, principle of increase of entropy, you have studied in BME up to this point. So we go beyond this. We study about availability and unavailability and irreversibility, and then we go to third law of thermodynamics. Okay, this is with second law of thermodynamics. So once we study the first law and second law, you might have heard about what are called as perpetual motion machines. People have fascination about it. So what is this perpetual motion machine means? Which runs forever, eternally. So whether that such thing exists or not. So thermodynamics first law and second law says such engines are not possible. But people have worked on it. Suppose they came with some hypothetical machines. So some of the perpetual motion machines I'm showing here, and later we can have some videos also. If you go to YouTube and just search for perpetual motion machines, you can have good videos. So here there are some perpetual motion machines shown here. And if you see this ball and magnet, so because of the magnetic power, it goes up. But because there is a hole here, it falls down. By gravity, it comes down and comes out. And again, by magnetic power, it goes up. And it continuously goes on and on and on. This is one of the perpetual motion machines people call it. And here also there is a wheel. If you see, there are a number of balls. And so theoretically, what they say is these balls which are away from the center, this brings out bending moment or moment onto the wheel, and it tries to pull down. There is nothing, so there is a force imbalance, and this moment makes it turn around so that these balls will again come down and it goes far, and continuously there will be some force acting on that, and there is a moment acting on that which is converted to torque, and then it is continuously rotated. So there are some more here. Here also you can see there are some things like this, and here some weights are there. because these weights are away from the center. Again, it cools down and it tries to rotate continuously. And again, there is another this is continuous flow you will be having. Okay, here this is the end of the tube, and there will be continuous water flowing down. So there will be flow going up because of the potential energy, and it goes up and it falls down, and there will be continuous rotation of the water around this. This is also perpetual motion machine. There is another called moving drinking bird, perpetually moving drinking bird. This is one of the toy-like things which can be purchased from outside, from fancy stores. You can have this. These two birds will be continuously moving up and down. There is no energy, there is no battery, there is nothing, but still it moves. So people say this is some of these people say that these are perpetual motion. But anyhow, we know theoretically it's not possible. So what is the secret behind this perpetual morning drinking bird? That we will discuss later. And then we'll talk about ideal gas and real gas. So in thermodynamics, so whatever you have taught in DME, we deal with ideal gases. So ideal gases are the ones which satisfy Boyle's law, Charles' law, and the ideal gas equation of state CV equal to RT, like that. And but all gases are not ideal gases. We know that's why we call it as ideal. So, but real gases act like ideal gases under some conditions, like low pressure and high temperature. But if the ideal gas laws are not satisfied, then what equation of state we have to use? So we have various things that we'll discuss. So relation among specific heats, internal energy, enthalpy, and analysis of isochloric, isobaric, isothermal, isentropic, isenthalpic processes. Actually, all these things we'll do in the second chapter itself. And then representation of the above process in TV plane and TS plane, that is pressure, volume, and temperature entropy plane, and determination of work, heat, entropy, enthalpy changes in the above processes, and characteristic equation of real gas. So here these two topics are new now. The top five topics are already learned in your second chapter. So characteristic gas equations of real gas, the real coefficients, law of corresponding states, and then compressibility factor, generalized compressibility chart. These are related to real gas. So just some of the equations I can show you here, real gas equations of state. One is the popular one, which is Van der Waals equation, and there are some other real gas equations of state, like Lick-Fong equation, the real equation of state. So we'll see what are the importance, how can we use them when we do the calculation of properties or solve. Then we have ideal gas mixtures. So when you have a mixture of different gases, so first we have to do gravimetric analysis and volumetric analysis. And then there are Dalton's law of partial pressures and the Amicott's law of partial volumes and mole fraction, volume fraction, evaluation of properties of gas mixtures. So if I have some properties of one gas and another gas with another properties, when they are combined, what are the properties of the mixtures, and what type of mixing it is, adiabatic mixing or non-adiabatic mixing, and how to deal with different types of mixes of gases. And when the mixes of gases are in a closed system, how it behaves, and when gases are mixed in a steady flow, how it behaves. Those we will study here. You can see the activity behavior of gas mixtures. So this is Dalton's law demonstration. This is the Amicott's law demonstration. If I have two gases at different pressures with same volume and temperature, and if they are combined to have the same volume and temperature, then the pressure will be the total of these two pressures. So that is called as Dalton's law of partial pressure. In the same way, if two gases at the same pressure and temperature are combined together to have the same pressure and temperature, the total volume of the mixture will be the sum of the partial volumes. This is called as Amicott's law of additive volume. So in the same way, if you have this is like adiabatic mixing. If I have two gases with a partition, and if I remove the wall, and when they are combined, so the total number of moles will be N1 plus N2, and the total volume is V1 plus V2. And if I want to have temperature and pressure, I have to use this formula. This is what is called as adiabatic mixing. And we can have steady flow mixing also. If you have a mixing chamber, one gas entering with M1 dot mass into from one inlet, and another gas with M2 dot inlet and entering. And if it is coming out with uh, different conditions, so how to find out the conditions of the mixture? So this is just an example of mixing chamber. If hot water is going from one side and cold water from one side, and it is coming out. So I have to know what is the temperature or conditions of water that is coming. This is mixing of gases and steady. Then I talked about fuel substance and what is fuel substance and all. And so if it is not a fuel substance, then there will be some other subjects we have to learn. But here, which is pure substance, which is not pure substance, we have to know. And one of the pure substance which we concentrate on is steel. And how to, because this is not an ideal case, and I cannot use all equations of state and all. Then how to find out the properties of the steel? And there is what is called as Mollier chart. So Mollier chart we can use, or we can use relations we have to use. And you can see, so these are PVT surfaces. This also we are going to learn about. So how pressure, volume, and temperature are related in is given in 3 dimensions. And there are two types of fluids that exist. So one is water type and another is non-water type. So they behave in a different way. You can see the difference in the figures. We will try to understand and discuss what is the difference between these two. And water have peculiar properties. Because of that, uh, actually, if you see one of the property, when you keep water in a fridge, I have to leave some space on the in the bottle, so that why we have to keep is as water gets solidified or fused, the uh, volume of the ice increase. It is unlike and all other substances. When it is frozen, actually its volume decrease for all other substances. But for water, the volume increase. That's why the water may break. So that is one particular interesting property. And another interesting property is for all the substances, as pressure increase, the saturation temperature increase. They are proportional to each other. But the fusion temperature of the water, as the pressure increase, the saturation temperature decrease. This is one particular property is practically utilized in ice skating. So when you how you slide over an ice when you are standing on that its piece. So that comes because of that. So we will again deal with that later. Then how to find out the properties of the steam. There are some calorimeters are available, throttling calorimeter and separating throttling calorimeter. And how to measure what's called as dryness fraction. We learn when we study about the calorimeter. This is the Maurier chart. So as I told, because steam is a pure substance, any two properties give all the other properties. And because I have to use, I cannot use perfect gas relations. So they have developed two experiments, the Maurier chart. So if I know any two properties, I can get all the other properties. Here it contains constant temperature lines, constant pressure lines, constant specific volume lines, constant tight fraction, dryness fraction lines, and this is entropy and this is enthalpy. So vertical lines are constant entropy lines, horizontal lines are constant enthalpy lines. So any two properties give all the other properties. Then we deal with the 8 standard cycles. As I told, Otto cycle used in petrol engines, diesel cycle used in diesel engines, dual combustion cycles in IC engines only, but high-speed IC engines, and then Brayton cycle in gas turbines. So we study like this: Otto cycle, the engine and its cycle, diesel engine and its cycle, and this is a dual combustion cycle, high-speed diesel engines, and then we have gas turbine working with Brayton cycle. So these are the various cycles, and we do the cycle analysis. And with this, and Rankine cycle, this already you have studied, which is used in power plants when water or steam is the working substance. So this is the Rankine cycle. So these are the cycles we discussed. Okay, this is about a brief overview of the syllabus. And evaluation procedure, already I told you, weekly minus will be there, 20 marks every Saturday at 5 p.m. It will be multiple choice questions on that week's coverage, and mid-exam 30 marks, and exam 50 marks, and total 100 marks. Okay, this completes the session, what I want to cover about the subject. And questions, I don't know if you can ask, it's good if there is no problem of audio or video or something, you can ask some questions if you have.
Sir,
Yes.
is that the machines related to perpetual motion really exist? I mean, in practical thing, not in the theoretical.
Practically, even theoretically also, it won't exist. But sometimes people try to uh, uh, confuse you or create an impression that it exists. So there, as I told, there are some beautiful videos are there. You can see they have made, but actually they will keep some battery inside so that it will work. But you will not, you cannot see that battery, and you will feel that it is possible. They will make you feel that perpetual motions exist. But theoretically or practically, it is never existing. Thank you, Premchandra.
Yes, sir.
Okay, thanks.
Thank you.
Any other questions? So normally I close the lecture with some beautiful, inspiring stories. So we'll end with that, right? So just you see, a candidate for a news broadcaster's post, he has applied a candidate for a news broadcaster's post, and he was rejected because of his voice. He was also told that with his obnoxiously long name, he would never be famous. And he is none other than Amitabh Bachchan. And if you see another example, a small boy, fifth among seven siblings of a poor father, he was selling newspapers in a small village to earn his living. He was not exceptionally smart at school, but was fascinated by religion and rockets. And the first rocket he built crashed. And missile that he built crashed multiple times, and he was made a butt of ridicule. He is the person to have scripted the space odyssey of India single-handedly. He is none other than the great Abdul Kalam. So whatever be the financial position of us, and many people think that because I don't have money, I don't have opportunities, I cannot grow. Other people are lucky, I am unlucky, like that. So we should not think like that. In the same way, sometimes when you face one or two failures, we think that, okay, we cannot do, we are, luck is not my side, there is no way to be successful, and other people are lucky. So that is also, you can, if you see the personalities, the great inspiring personalities, they face so many failures in the initial stages. But that's why people say uh, success is not in not having failures, but in rising every time we fall, right? So falling naturally happens with everybody, but the rising will be done by only the people who are successful. So always we should not lose heart whenever you have some problem in the life or you have some failures in the life. We always have to try to get up, and at one or two failures after that, you are going to be successful like any other person. Okay, thank you very much. This is the end of the lecture, right? And I think I have completed before 1 hour. It is
Sir, one question.
Satish, okay, ask me.
What you through mail or
I could not hear. And another thing,
can we get the PPT?
don't hesitate. And I will try to be as friendly as possible, right? So don't hesitate to talk to me or message me anything, right? It need not be online, it can be offline, anything. Okay, what
Will
is
you
the doubt,
share your PPT,
Satish?
sir?
Anything anybody want to ask? No doubts? Could you listen to me?
Sir, they are asking, can we get the PPT?
PPT, yeah. Okay, I will send the PPT, no problem.
Thank you, sir.
And I think if it is recorded, that recorded video also I can send. Okay. Okay. All the best. We'll meet again in the next class. So we'll try to sort it out whatever problems we have. I hope the later classes will be better. Thank you everybody.